Knowledge is free, perspective is expensive. This quote embodies much of the value you will gain by completing this course. Together, we will journey through the science of cannabis, discover what is true, what has been exaggerated, and what we still need to discover. Using the lens of complex systems is absolutely critical to us to allow for the full appreciation of this controversial plant. Before we dive fully into cannabis, we need to build a base structure of understanding for how we as humans obtain objective knowledge. Since most cannabis research has been done using incomplete linear methods, and this course explores cannabis via a complex systems perspective, a brief history of science will get us up to date on knowledge discovery and the limits to reduction. So the goal of science is to understand natural phenomena. We want to understand natural phenomena so we can make predictions and then design objects and systems which can improve our species. An important note is that although humans formally do science, every species makes predictions based on molecular inputs from the internal and external environment. My cat tests his predictions of where the bird will be when he is chasing it through the trees. His neural patterns are enhanced as positive feedback for successful hunts. Our ability to understand and make predictions has been formally defined as science. The mechanisms of science did change during the years. This subject could easily be its own course. So to save time, I will speak to the bare bones advancements. Induction is a good idea. It's how we started. Testing ideas that we talk about is even better. Testing ideas formally using standardized methods is even better. And currently, we can mostly only know things as a probability of truth. The formal science we were taught in high school, and is still being taught in high school, is referred to as reductionism. By isolating and testing one variable while trying to keep everything else the same, we can draw conclusions and learn things. What we can formally state is some probability that an idea is true or false based on a level of significance for an effect size based on previous observations. The larger goal being to take these many smaller experiments of single aspects and add them up to form a working understanding of the system. Science has largely existed in this reductive form since the time of Sir Isaac Newton. So while this was extremely helpful for progressing our species, we are starting to understand that our tools need to be updated and we can't predict how systems behave, which, again, is the point of science. Okay, now that we have reviewed hypodeductive science, we can start to explore complex systems. So our first step in understanding complex systems would be to define systems. Then we can go through the differences between linear and nonlinear systems and explain why linear functions are incapable of describing complex behaviors. Since the prediction from understanding is the desired actionable result of science, we will speak to predictability in chaotic systems. This will lead us into the idea of sensitive dependence on initial conditions. Systems are collections of objects which operate together to form the whole. The whole essentially is an emergent property. Most everything is a system. Cars, computers, churches, the economy, the Milky Way, all living creatures. These are all systems. Going back to linear systems here for a moment, linear systems are relatively simple in comparison to complex systems. They are simple because the internal rules which govern linear systems only allow for behaviors and actions that are limited by a fixed ratio of input to output. This is why evolution selected living organisms whose design was able to respond and adapt to a changing environment, especially in Earth's early history. Linear systems assume and require homogeneity, which basically means sameness. Linear systems are deterministic, which means that the inputs interact and can be described with a mathematical function to produce a predictable output. They also display additive results, which is an emergent property of its inherent working parts. So let's examine linear versus nonlinear graphs. Linear functions and systems give outputs, i.e. behavior, like the orange line on the graph, typically a straight line. Nonlinear functions and systems display much more complex behavior. Though the blue line may not appear significantly more dynamical than the orange, it is. Note the curvature, which changes differently as a behavior compared to straight lines. We can see that the blue line is not a one-to-one output among the x and y variables. It is, by definition, more dynamical. Having response types of curves that can be extended, altered, and recombined leads to better descriptions for more diverse behaviors. Having more tools to describe more behaviors is the name of the game in science, right? Also, being sensitive to inputs and outputs is useful. Again, not always having a fixed input to output ratio allows for more dynamic responses. Let us do a thought experiment for a moment. What if you went to the doctor and the only test done was a measure of your heart rate? And from this measure, the doctor prescribed your entire health plan. Would you be okay with your health plan using this single measure? I would hope not. There's much more to health than somebody's heart. Perhaps a football analogy will hit home. How accurate would the predictions be from an offensive coordinator who only took into account 10 of the players on the football field? Not very well. Similarly, research that only uses THC or THC analogs has not been shown to recapitulate the medical effects to the same extent as those using whole cannabis extract. We will speak more to this later when we learn about the endocannabinoid system. This is an important economics quote. When measures become targets, they cease to be a measure. So essentially, this alters the system and perverts its function. Measures and targets can lead to unintended consequences, resulting in qualitative shifts of agent behavior, i.e., gaming the system. So what are the pitfalls of using Newtonian reductionist linear thinking? Well, since 2001, we've had a fully mapped database for the human genome, and this has not produced the medical marvels it had promised. Not because DNA is unimportant, but because biological organisms don't run linear programs. The decision-making that occurs is an emergent result from networks of genes and proteins and molecules interacting. Economies are complicated, and prediction requires probabilities and iteration. In the 1800s, the field of economics started to incorporate linear mathematical paradigms with some initial success. Though still used to some extent, the field of economics has also incorporated many nonlinear techniques. Indeed, it is well known that the physics guys who studied nonlinear statistical mechanics are the ones who implemented these paradigm shifts on Wall Street. So let's do a quick recap before moving on. All animals make and test predictions. Humans have formalized this process and call it science. Now, the goal of science is to obtain objective knowledge so we can make accurate predictions about systems. Most systems do not display linear behavior and are much more dynamical. Reducing systems to single measures and straight lines can lead to inaccurate predictions. So up next, I'd like you to be able to describe the predictability of chaotic systems and to define sensitive dependence on initial conditions. What we observe in complex systems is that the outputs are not proportional to the inputs, that the outputs can be chaotic and quite often counterintuitive. These internal mechanics, or processes within functions, is what allows for the description of complex systems. Nonlinear systems can be composed of multiple equations that interact to form functions, and these functions describe behaviors of systems. Later, when we introduce phase planes, it will be easier to visualize and understand how these systems more accurately represent operational conditions that occur in reality. In the last slide, it was stated that nonlinear systems display chaotic behavior. Chaotic behavior indicates and translates essentially into less prediction. Now, it's not that the system is impossible to predict, it's that we can't predict because we don't understand the system that well, or well enough, or we can't measure enough to predict the patterns being displayed. At the far edge of math and complex systems is a new field of algorithmic information dynamics, which improves upon information theory by way of using random computer programs to determine the generational mechanism for data strings. This field is very exciting as it recombines causation with truth and proof, which in mathematics was formally separated in the 1900s. Essentially, though, it appears that nothing is random, and all knowledge can be thought of as compression of information into its generational mechanism. It is important to note that complex systems don't only display chaotic behavior. Complex systems are shown to exist as either stable or chaotic, and that there is a distinct phase transition between these two conditions, and it is often referred to as the tipping point. Again, an important point is that chaotic does not mean random. A chaotic system is less predictable, but it's not necessarily unpredictable. There are a nearly infinite number of mathematically true statements we can make about any system in chaos. For example, the weather is often chaotic, but it's not infinitely possible. Earth's weather systems can never produce temperatures of 300 degrees Celsius, at least with the sun in its current operational state. And the Earth can't have snowy conditions when it's 90 degrees Celsius outside. A great example of a complex system that often shows phase transitions, here, quite actually the transition between different phases of matter, is the weather. If you were to hear, there is a 60% chance of rain, what would you think? Your thought would likely be that today there's a 60% chance that it will rain. If you were a bit more complete, you could say something like, today there is a 60% chance that the moisture in the air will interact in a way such that a phase transition will occur and some moisture will precipitate. You would still be missing a vital piece of information. As in, what do you mean by 60%? What the meteorologists do not state is that a 60% chance of rain means that given these conditions, historically, there has been a 60% chance that it will rain. That is much different than saying 60% chance of rain. It means that based on our data set, based on what we can measure, 60% of the time, it has rained. Weather shows sensitive dependence on initial condition, which is the butterfly effect. Many Americans have heard of Ashton Kutcher, and even more people have likely been exposed to the idea of the butterfly effect. The butterfly effect would be the common manifesto for those speaking to sensitive dependence on initial conditions. It quite actually explains how small differences in the starting conditions of a system can lead to drastic differences in outcome or predictability. The concept of sensitive dependence is very important for our understanding of cannabis. The idea of predictability hinges on our understanding of how the system works. Think for a moment how much harder a game of pool would be if the balls responded differently depending on the time of day it was, or what beer you were drinking, or if a butterfly flapped its wings 10 minutes ago, and that would impact your shot. I doubt the game of pool would be as popular. Humans crave predictability. It is a requirement for a functioning society. The logistic equation is often used to teach the concept of sensitive dependence on initial conditions. The goal for this section is not for us to spend hours going through the mathematical proofs for the logistic equation, but rather to gain a conceptual understanding of the function, so that we can use it to learn about certain aspects that are inherent to complex systems. The logistic equation is an iterated function that accurately, not exactly, describes the behaviors we see for population growth under certain conditions. It's a function that tells us what next year's population would be based on this year's population size. The units of measurement are discrete, so we are given the results at the end of the year. The initial condition is represented So the initial condition, x0, is percent of the annihilation population. A is the annihilation population, and essentially that's the carrying capacity, or the maximum number of organisms that area can hold. Now this is dependent on the species and the area. It's also dependent on R, which is the growth rate. The growth rate of the population can be adjusted to fit real-world data. For example, when there are periods of time or in history when areas experienced especially experienced large amounts of precipitation. This would in turn affect plant growth and then therefore affect the energy availability to an ecosystem, and therefore how fast or slow a population can grow, and what the annihilation population could even be. So these variables can be adjusted. This program shows how different growth rates affect the behavior of the system. Let's explore a few values. A growth rate of 2.1 and a growth rate of 3.1. So for the growth rate of 2.1, we see a stable population near the starting condition of the annihilation population, which is 0.5. The growth rate of 3.1, we see a population that oscillates cyclically between 0.56 and 0.76 of its annihilation population. Let's try 2.6 and 3.6. Here we see that when the growth rate is 3.6, the population changes do not seem to have any sort of repeating pattern. In contrast, a growth rate of 2.6 shows a small initial increase in the population size and then settling down into a fixed state at 0.62. What about two very similar starting conditions, say 3.6 and 3.7? We see patterns of population growth that diverge right away at year 1, and by year 4, entirely different behavior is seen between these two starting conditions. What about a more distant future? We see at year 13 a convergence of behavior, but does it continue? Let's find out. Instead of 20 time steps, I will do 40. Here is where we're starting to see the congruence of behavior. Year 20. No, the congruence does not continue. If you play with this program and others like it, and do many conditions, you start to notice patterns of behavior for these systems. They are not exactly the same, but there does appear to be something we can say. For instance, when a population nears its annihilation population, it does not stay in that position very long. One important note about this program that I am showing you is that it does not allow me to adjust the initial starting conditions. In every example we've seen so far, the population started at 50% of its annihilation population. As you might infer, adjusting these starting conditions leads to radically different behaviors. However, there is still some regularity to what is observed. This regularity is what we will discuss in the next unit. So, a quick recap. The outputs and behaviors for complex systems can be chaotic, which means predictability is limited and impossible to describe with linear functions. Complex systems show sensitive dependence on initial conditions. We can use the starting conditions to predict future outcomes. The logistic equation is a model for population growth that demonstrates the butterfly effect, and it is not possible to measure with enough accuracy to predict behaviors within complex systems.